17 January 1966. Palomares, Almeria Province, Spain. A White House Situation Room update is drafted hours after a Strategic Air Command bomber breaks apart over southern Spain. The first confirmed technical detail is not nuclear, but high explosive behavior inside two weapons. The United States has procedures designed to prevent a nuclear yield even in an accident, yet low-order conventional detonations can still create a radiological emergency by dispersing plutonium. The memo warns that 2 of the nuclear devices experienced a low-order high explosive detonation, meaning no nuclear reaction but a possible radiation hazard. Within hours, Spanish authorities are demanding tight press control, and the US is running 2 operations at once, a land contamination response and a deep-water search for a missing weapon, under diplomatic pressure that will soon suspend US overflight rights. They did not yet know that this recovery would take 80 days and reshape airborne alert policy forever. Mid-January 1966. Strategic Air Command Headquarters, Offutt Air Force Base, Nebraska. A mission planning board displays call signs, refueling windows, and tanker tracks across the Atlantic and Mediterranean. The routine is defined by repetition, multiple refuelings per sortie because the mission length demands it. Operation Chrome Dome is continuous nuclear-armed bomber flights, a visible deterrent kept aloft around the clock. The system is sold internally as controlled deterrents, aircraft crews and weapons kept within procedural guardrails. But the same program embeds a single high-risk dependency, aerial refueling. The mission is safe only so long as the bomber and tanker geometry remains stable for seconds at altitude. Every refueling event is a coupled operation: boom extension, closure rate, contact pressure, fuel flow, disconnect. Each phase must succeed. The B-52G and KC-135 tanker function as an integrated system. The bomber carries 4 hydrogen bombs, the tanker carries fuel. Between them is a telescoping boom and human judgment. Strategic Air Command oversees the network. The United States Air Force provides tanker support. Spain provides bases and overflight permissions under bilateral agreements negotiated in the 1950s. More on Airbase and Zaragoza are part of the support infrastructure. The operational choice, continuous airborne alert, multiplies refueling events. Refueling events multiply exposure to a single failure mode. A declassified Department of Defense summary states, all detonations involved only conventional high explosives. Only 2 accidents, those at Palomares and Thule, resulted in widespread dispersal of radioactive materials. The document stresses there was no inadvertent nuclear detonation. The danger is not yield. The danger is rupture and contamination. On 17 January 1966, that failure mode triggers not only an aviation disaster, but a contamination control operation and a missing weapon problem that will take 80 days to close. 17 January 1966. Payload context over the Mediterranean. Weapons later recovered near Palomares. A schematic diagram lies on a light table in a technical review, B-28 family diagram beside an incident checklist that separates nuclear yield from high explosive event. Nuclear weapon safety aims to prevent a nuclear detonation in an accident. That expectation holds. But Palomares demonstrates an uncomfortable reality. A non-nuclear accident can still produce long-lived contamination if the conventional explosive components rupture the weapon and disperse nuclear material. The B-28 is a thermonuclear weapon with multiple safety interlocks. An accidental detonation requires a precise sequence: arming, altitude sensing, fusing. The design prevents nuclear yield even under severe impact or fire conditions, but the conventional high explosives used to compress the nuclear core can still detonate. When they do, plutonium and other materials can be scattered across terrain. Dose and activity are different measurements. Dose, measured in sieverts, is biological effect. Activity, measured in becquerels, is decay rate. For plutonium, the critical pathway is often inhalation or ingestion. Plutonium is an alpha emitter. Alpha particles do not penetrate skin but cause severe damage if inhaled or consumed. External gamma exposure is not the primary concern. The cleanup question becomes, where is the plutonium, how much, and what are the pathways? The Department of Defense summary is direct. All detonations involved only conventional high explosives. Safety design avoids nuclear yield, but a low-order or full high-explosive detonation still forces environmental remediation and long-term monitoring. The weapons will not behave uniformly. 2 rupture and contaminate. 1 is found relatively intact, and 1 disappears into the sea. 17 January 1966. Over the Mediterranean near Palomares. Bomber at approximately 31,000 feet. Collision around 10:30 a.m. A command post logline captures the sequence. Initial report, confirmation, dispatch of a disaster control team. The refueling contact should end as a routine fuel transfer. Instead, collision destroys the tanker and breaks the bomber apart. 7 crew members die immediately. 4 survive and bail out. Major Larry G. Messenger, the B-52 pilot, is later quoted recalling the collision mechanics. The tanker boom makes contact, structural failure follows, the bomber disintegrates, debris begins falling. Major General Delmar E. Wilson is documented traveling to the scene with a disaster control team from Torrejon Air Base near Madrid. The response is immediate, but the problem is dispersed. The mechanics are straightforward. During refueling, the tanker's boom contacts the bomber. Something fails. The aircraft separate violently. Both are lost. Wreckage falls across a wide area. 3 impact zones on land. 1 suspected sea entry. The fall pattern becomes an accounting problem. How many weapons, where, intact or ruptured? Early search is not dramatic. It is methodical. Teams walk grids. Instruments scan terrain. Visual searches locate large components. Within 24 hours, 3 bombs are located on land. 2 have experienced conventional high explosive detonations. Plutonium is dispersed. The 3rd is found relatively intact, but the 4th is missing. It is presumed to have entered the sea. Immediate accounting drives 2 parallel missions: recover weapons for security and survey contamination for public safety. The missing 4th weapon becomes a strategic and diplomatic liability that will dominate the next 2 months. 17 to 18 January 1966. Palomares area. Coordination between Torrejon Air Base and Madrid. A temporary command post is established. Perimeter tape, controlled road access, and the first radiological survey routes being assigned. United States planners want secure and quiet. Reality is a populated farming area and a host government that must answer to its own security and credibility concerns. United States Air Force disaster control teams arrive. Spanish civil authorities coordinate access and public messaging. The United States Embassy channel opens. This is not a unilateral military operation. It is a combined response problem from the first hours. Secure the area means in practice, establish cordon zones, restrict entry, locate weapon components, and start initial contamination screening. Field log sheets, sample labels, and chain of custody notes become the documentary record. Health physics teams begin radiation surveys. Geiger counters scan the ground. Air samplers run continuously. Soil samples are collected in numbered bags. Each sample is logged with location, time, and surveyor initials. The process is slow and deliberate. The terrain is agricultural. Tomato fields, farmhouses, and irrigation ditches complicate access. A declassified diplomatic history document frames Palomares and Thule as ambassador-level crises. The accidents are not only technical events, they are political events. Early custody decisions determine whether Spain views the response as cooperative or unilateral. That perception sets the tone for later negotiations. The first land recoveries answer, "Where are the bombs?" But they also reveal the worst operational asymmetry. No nuclear yield, yet contamination is real, and 1 weapon is still missing. Spain sees an uncontrolled nuclear object in its waters. The pressure begins immediately. 17 to 20 January 1966. Palomares farmland and nearby terrain. A laboratory survey note records the shift. 2 weapons impacted, and their conventional explosives detonated. The radiological problem moves from find objects to map contamination. The public might expect hydrogen bomb to mean nuclear. Blast! The documented outcome is different. 2 conventional explosive events disperse plutonium-bearing material and contaminate approximately 2 to 2.6 square kilometers. The reported area varies by measurement method and reporting boundary. Dispersion becomes dust and hotspots because of wind, particle size, and deposition patterns. Contamination is not uniform. Activity concentrates in certain areas. Sampling density must be high to capture the variability. What does contaminated mean operationally? Activity in soil, measured in becquerels per square meter. Patchy distribution. The need for repeated sampling. Health physics teams carry portable instruments and collect soil cores. Some readings are near background. Others are elevated by factors of 10, 100 or more. The highest readings are found near impact craters, where the conventional explosives detonated. Secondary scatter zones extend downwind. Rocky slopes and vegetation complicate removal. The Department of Defense summary is clear. Only conventional high explosive detonations occurred. Palomares is a dispersal case, not a yield case. But dispersal creates long-tail commitments. Plutonium-239 has a half-life of 24,000 years. Americium-241, a decay product, has a half-life of 432 years. The contamination does not disappear, it must be managed. Cleanup will hinge on a documented decision boundary. Soil above a threshold is physically removed and shipped. Soil below the threshold is mixed or ploughed. That contrast will later fuel resentment and renewed cleanup demands. Late January to February 1966. Palomares survey grids and sampling program. A health physics workflow emerges. Sample collection, labeling, transport, assay, mapping. A threshold value becomes the operational hinge. Officials want a clean safe or unsafe statement. The measurement reality is graded categories and remediation choices with trade-offs. A cleanup criterion is established. Soil above 1.2 megabecquerels per square meter is drummed and shipped. That is 1.2 times 10 to the 6th becquerels per square meter, approximately 3.2 times 10 to the minus 5th curies per square meter. 1 curie equals 3.7 times 10 to the 10th becquerels. The conversion is provided once for clarity. Soil with lower contamination is treated by ploughing or harrowing. Hand removal is used on rocky slopes above 120 kilobecquerels per square meter. United States and Spanish authorities coordinate the sampling program. Measurement practices will be referenced in later assessments and compensation frameworks. Field teams mark grid squares. Samples are taken at regular intervals. Each sample is analysed for plutonium and americium isotopes. Results are plotted on maps. The maps show hotspots and clean zones. Air sampling is conducted to assess inhalation risk. Filters are analysed for airborne plutonium. Monitoring continues for weeks. The data guides removal decisions. Threshold decisions determine volumes removed, shipments, and the long-run argument over how clean is clean. The numbers that will define Palomares are not blast yields. They are becquerels per square meter thresholds, hectares treated, and barrel counts. And those counts do not agree across sources. February to March 1966. Palomares staging areas, shipment chain to United States disposal sites. A loading line is established. Contaminated soil and vegetation packed into standardized drums. Manifest are signed. The remediation becomes a logistics pipeline. Cleanup is imagined as a local fix. The documented reality is international transport. Spanish soil moved to United States facilities for disposal. A 1975 Palomares summary report references 4,810 barrels shipped. A peer-reviewed overview also cites 4,810 barrels and places the total shipped soil and vegetation around 1,400 metric tons in some analyses. Wikipedia separately mentions 6,000 barrels produced under one accounting description and reports approximately 1,750 tons removed. These are different accounting boundaries. What counted as barrels? What counted as radioactive soil? Which phases were included? Some totals include only high-activity material drummed for shipment. Others include lower-activity material treated in place. The variation reflects how different agencies defined scope and completion. Each barrel is a standard 55-gallon steel drum. Contaminated soil is scooped, shoveled, or scraped into the drums. Lids are sealed, radiation labels are affixed, manifest record drum number, estimated activity, and origin grid square. Trucks carry the drums to a port. Ships transport them to the United States. The final destination is a licensed disposal facility. The shipment solves one problem, removing high-activity material. It creates another, a permanent record and long-term political symbol. Spanish earth exported as nuclear waste. While barrels leave by ship, the missing bomb does not move at all. It is governed by seafloor physics, not truck schedules. February to March 1966. Madrid and Palomares coastline. Public reassurance event on 8 March. A press staging problem emerges. Camera positions, official statements, and the need to show normalcy while recovery remains incomplete. Governments want reassurance, but reassurance competes with ongoing restricted zones, continuing surveys, and a missing weapon at sea. Spanish Minister Manuel Fraga Iribarne and United States Ambassador Angier Biddleduke publicly swim to signal safety. The event is documented in major summaries. The image is widely circulated. The message is clear. The water is safe. The land is being cleaned. Normalcy is returning. But the operational reality is different. Restricted. Zones remain. Surveys continue. The missing weapon is still underwater. The Spanish state information apparatus controls press access. The United States Embassy manages military public affairs. The declassified diplomatic history highlights ambassadorial burdens in nuclear accidents. These are not routine incidents. They are crises that involve sovereignty, security, and public trust. This chapter explains the political risk of unfinished recovery. An unrecovered thermonuclear weapon in Spanish waters is a sovereignty issue. Spain's government faces domestic pressure. Why is a foreign nuclear weapon in Spanish territory? When will it be removed? What are the risks? The operational consequences are real. Pressure builds on United States basing and overflight conditions. Spain suspends overflight rights temporarily. The suspension is documented in declassified summaries. Host nation demands will shape future policy. Public messaging is not cosmetic. It influences whether Spain tolerates the time required for deep water recovery. Under the surface, the missing bomb will be located, then lost again during recovery attempts. Found becomes a new operational failure state. 22 January to March 1966. Mediterranean off Palomares. A Navy meeting note records the creation of a technical advisory group to coordinate resources, specialists, and search strategy. The expectation is that sonar plus a search grid produces a quick recovery. Reality is limited precision, uncertain drift and fall dynamics, and complex seafloor terrain. The technical advisory group is chaired by Rear Admiral L.V. Swanson. Dr. John P. Craven and Captain Willard Franklin Searle are documented members. Fisherman Francisco Simo Orts is documented as a witness who reported what he saw and later assist the recovery effort. His account helps narrow the search area. The search process is broken into steps. Witness Q provides a probable area. Sonar sweeps scan the seafloor. Candidate contacts are identified. Confirmation attempts follow. A parachute tail plate is recovered. It shapes drift assumptions and supports the hypothesis that the weapon went to sea. Sonar has limitations. Target discrimination is difficult. Rocks, debris, and seafloor features produce similar returns. Depth is a hard constraint. Divers cannot operate below certain depths. Remote methods must be used. The Woods Hole, Oceanographic Institution's History of Alvin, records that the bomb was first located and then lost during lifeline attempts. The creation of the Technical Advisory Group formalizes the sea problem as an engineering mission, not a local search. Stakes rise, visibility increases, the timeline becomes blunt, the bomb is located, then lost. It slides down slope. The search must restart at greater depth. March to early April 1966. Seafloor off Palomares. A dive plan and checklist define the mission. Bottom time, visibility constraints, and the difference between search and verify. The public expects a dramatic recovery. The operational reality is incremental. Alvin helps convert ambiguous sonar contacts into visual identification, and identification still does not guarantee retrieval. The Woods Hole, Oceanographic Institution's history of Alvin provides the clearest timeline. The bomb was first located 15 March. It was lost during a lift line attempt. It was relocated to April. It was recovered by CURV 7 April. The sequence is documented. Alvin is a deep submergence vehicle. It carries a pilot and observers. It has external lights, cameras, and manipulators. It can operate at depths divers cannot reach. The mission depth is approximately 910 meters, or 2,990 feet. The figure appears in Woods Hole materials and related summaries. Depth changes everything. Diver limits are exceeded. Tether loads increase. Seafloor slope risk is real. Alvin provides eyes and improves localization. Visual confirmation allows the recovery tool to do the attachment work. But Alvin cannot lift the weapon. That requires another system. Each dive is limited by battery life and bottom time. The search area is large. Most dives find nothing. When the weapon is located, the next challenge is attachment. The seafloor is uneven. The weapon is heavy and awkward. Early lift attempts fail. The weapon slides downslope. The search must restart. Found is not closure. The timeline emphasizes loss during attachment attempts. The next chapter becomes a salvage engineering problem under diplomatic scrutiny. 7 April 1966. Recovery ships off Palomares. Custody chain back to United States. Cable tension, deck crews, and a controlled lift define the operation. Success is measured by continuous control rather than speed. The expectation is that recovery ends the incident. The reality is that recovery ends only the missing weapon phase. Land contamination and political aftermath remain. CURV is the cable-controlled undersea recovery vehicle. It is an unmanned system. It executes the attachment and lift mechanics at depth. The Woods Hole. Oceanographic Institution records the key date, recovered by CURV 7 April. The system is lowered from a surface ship. Operators control it via cable. Cameras provide visual feedback. Manipulators attach lift lines to the weapon. The lift is slow and controlled. Tether tension is monitored continuously. Deck crews stand ready. The weapon is brought to the surface. Once on deck, custody is restored. The weapon is secured. Transport is decided. Statements are prepared. Navy salvage teams and the Woods Hole submersible program work together. The operation demonstrates the value of combined capabilities. Alvin for search and localization. CURV for attachment and lift. The integration is not seamless. It requires coordination, communication, and repeated attempts. But it succeeds. Recovery allows the United States to claim control over the full inventory. All 4 weapons are now accounted for, but the narrative is locked in. Contamination was real. The remediation choices will be judged for decades. The incident becomes an accounting argument. Barrels, hectares, thresholds, and monitoring. The numbers vary by source and fuel later disputes over final cleanup. 1966 to 2000s. Palomares monitoring zones, evolving assessments and veteran exposure questions. A monitoring report years later records repeated surveys, wildlife findings, and the administrative reality of restricted plots. The early expectation is that soil removal and ploughing settle the issue. Later studies and reporting show continuing concerns. Residual contamination in certain areas drives continued restrictions and debate. Wildlife measurements are discussed in later reporting. Plutonium is found in soil cores, vegetation samples, and animal tissues. The levels are low but detectable. Long-lived transuranic elements persist. Activity does not disappear. Spanish technical bodies and United States counterparts coordinate monitoring. The Veterans Affairs Public Health framing addresses exposure context for military personnel who worked on the cleanup. Bioassay programs track internal contamination. Dosimetry records are reviewed. Compensation frameworks evolve. The operational meaning of long-lived transuranics is clear. Activity persists. Risk is pathway dependent. Monitoring focuses on soil activity. resuspension potential and bioassay where applicable. The question is not, is there any plutonium? The question is, does the remaining plutonium pose a risk? Comparisons are modest and factual. No specific sievert values are claimed without primary sources. The peer-reviewed history of dose, risk and compensation shows how assessments evolved. This became a multi-decade evaluation problem. Residual contamination transforms Palomares from accident response into stewardship. It influences trust and land use planning. The story does not end in the 1960s. Spain returns to the question of removal and disposal decades later, seeking a definitive agreement rather than indefinite monitoring. 2015 to present framing. Policy look back to 1968, termination of airborne alert. A diplomatic document on a podium contrasts with a Cold War policy line item. What changed after Palomares and Thule? Governments periodically signal intent to resolve the remaining contamination question. The operational reality is slow negotiation over cost, disposal pathways, and definitions of final cleanup. The Department of Defense Mishaps Report states airborne alert was terminated in 1968. The document cites accidents, particularly Palomares and Thule among the drivers, along with cost and ICBM survivability. The policy consequence is documented. Palomares contributed to the end of a strategic posture. 19 October 2015. Madrid, the United States and Spain sign a statement of intent to negotiate a binding agreement to further remediate Palomares and arrange disposal of contaminated soil in the United States. The statement signals political alignment but not immediate execution. Later reporting notes that a final binding agreement and removal actions did not promptly follow. Palomares demonstrates that no nuclear yield is not the same as no nuclear liability. The decisive variables are documentary: becquerels per square metre thresholds, hectares treated, barrels shipped, days to recover, and how institutions document uncertainty. The story is not about explosions. It is about accounting, sampling, thresholds, and logistics. It is about whether institutions can convert measurements into trust. Palomares did not produce a nuclear detonation, yet it produced an enduring nuclear stewardship problem, measured in contaminated soil inventories, monitoring regimes, and policy reversal on airborne alert. The numbers tell the story. The thresholds remain.